Let's look at the graphical solution of two variable linear programming problems. So we'll solve two problems for this. So graphically solve problem 1 of section 3.1. So we have a farming problem from before with Farmer Jones. And we basically make each of these equals. We make them equal signs and graph them. That's basically a graph of inequalities, and then figure out what side to shade, the bottom or upper side of it. You know, which side of the line you shade. And they'll make an inequality. You know, these are greater than or equal to or less than or equal signs in general as these right now, so we can easily shade. Like you don't have to do a dotted line or anything. Use a straight line because it's equal to it as well. Yeah, so that's the big step we do. The first thing is graph it out, figure out what our region is. So we do x1 plus x2 equals 7, then obviously if one of these variables equals 0, that's what we do. We find the x-intercept and y-intercept by setting one of them equal to 0. Well, it's x2 intercept this time and x1 intercept because x1 and x2 are the graph of the axis. So x1 equals 0, x2 equals 7 because that's all that's left, and same thing with x2 equals 0, x1 will equal 7 then. And one of the things we do is 0 plus 0 down here in green less than or equal to 7, so that means you shade below it. You shade the area that contains the 0, 0 point, and that's a really good check for stuff. We do 4x1 plus 10x2 equals 40. So x1 equals 0. We have 10x2 equals 40, which means x2 equals 4. x2 equals 0. 4x1 equals 40, so x1 equals 10. So you get 0, 4, and 10, 0. And if you do 0 plus 0, like you add 0 and 0 into it, you just get 4 times 0 plus 10 times 0, which is 0 plus 0 equals less than or equal to 40. Use the equality sign and the inequality symbol. And that's true. So you include the part of the graph that includes 0, 0 for that shading. Finally, 10x1 equals 30 means that x1 equals 3 in that case. So it's just the graph of x1 equals 3 for that, which is a vertical line on the x1 equals 3 point. So x1 always equals 3. And then 0 is greater than or equal to 3 is not true, so you shade the right-hand side here with the left because the area that does not include 0, 0. The point 0, 0. Okay, so you get all this work done and then you graph it. You take up a small axis and stuff, and it should be focused on the upper right side more than anything because of how it works. Try and focus on positive values. So you graph them using a standard. You take your two intercepts and then draw a line as well as you can. So I place like a little star in the color to make it simple. So includes 0, 0 for brown, which is the green also does. So here, about a star right here. So you shade. So for simplicity with these, the main thing you shade is like the one region that has all of them. That's the goal. So it has to be below this and this. So brown and green. So it's this area so far, and then the x1 equals 3. It's where where 0, 0 is not included. So it would be this whole thing. So it becomes this little quadrilateral with points A, B, C, D. So 4 points quadrilateral. And all solutions to the constraints, the feasible region that is, the whole feasible region is this little black quadrilateral here, which I believe would be just a trapezoid of some sort. Be a type of trapezoid, I believe. But we're not going to get into geometry. But yeah, there's a theory behind this that each of the corners, one of the corners will be the solution to the objective function. There's a theory behind it. So these 4 points are all we have to check, the four corners of the polygon, or whatever corners there are of the polygon edges, the points on the sides. Yeah, you only have to check them for the max function. Okay, so here we see that A, B, C, D. Well, A, D, and C are known because those are points. You know, D is just It's the point on the x-intercept where x1 equals 3 and x2 equals 0. A. Wait, we don't know A or B, remember. Those are intersections of lines, of two lines, each of them. But we do know D and C, because C is also an intercept. D and C are intercepts, so we know them when we did our calculations earlier. So C is going to be 7, 0, and D is going to be 3, 0. So we do intersect of each of them to find. So A, these are very quick and easy, generally. Like simple two-variable systems of equations, two equations, very easy to solve. So we have this equation, 10x1 equals 30. We do 1/10 times equation 2 to get just x1 equals 3. We have 4x1 plus 10x2 equals 40 as the other line. So we plug in x1, we get 4 times 3 plus 10x2 equals 40, and we solve like basic algebra skills. Then we get x2 equals 2.8, x1 equals 3. So the point A is 3, 2.8. And then the B intersect is same as right here. So A, B, so B here is the green line and the brown. What we do is equation 2 minus 4 times equation 1. That gets 6x2 equals 12 and x1 plus x2 equals 7. Does not change. So we get just x2 equals 2 by dividing both sides by 6. Then we plug in x2, we get x1 equals 5 by plugging that in. So because it would be x1 plus 2 equals 7, we get from x2 equals 2. So just subtract 2 on both sides, you get x1 equals 5. So 5, 2 is point B. C is 7, 0, and D is 3, 0, like I said earlier. Now we plug in A, B, C, D. We plug them into the Z function, the objective function. So it's 3 times 30 plus 100 times 2.8 will give you $370, and you get $350 from B, from 5, 2. C, which is 70, gives us $210, and 30. D gives us $90. So the highest value in a maximum problem or the lowest value in a minimum problem. This is maximization, so you get $370, the biggest, so point A is the one. So the optimal solution is x1 equals 3, x2 equals 2.8, max Z equals $370. So we get 3 acres and 2.8 acres. We get $370. Here's another problem. Leeway Chemical manufactures 3 chemicals, A, B, and C. These chemicals are produced via 2 production processes, so we're going to have to, basically we're going to have to set up the LPNs and solve it. One process, you have, this time there's 2 production processes, just 1 and 2, which I put a note here, let x1 equal number of hours of process 1 and x2 equal number of hours of process 2. Running process 1 for an hour costs $4 and yields 3 units of A, 1 unit of B, and 1 of C, so I noted those down. The running process 2 for an hour costs $1 and produces 1 unit of A and 1 of B. Those are the big things, those units that are produced. Because those are chemicals, A, B, and C, that we want. To meet customer demands, at least 10 units of A, 5 of B, and 3 of C must be produced daily. At least means greater than or equal to. We need at least these, so greater than or equal to 10, 5, and 3 for those. Graphically determine a daily production plan that minimizes the cost of meeting Leeway Chemical's daily demands. So daily, yeah, it's going to be by hours. We're minimizing costs, and it's like you're not going to get 24 hours. Yeah, that's not going to be part of the conversation. It's going to take way less than that, by default. So the daily production plan, that's just a note I'd say in my head. Like sometimes you're like, yeah. That's why it's number of hours of process 1, number of hours of process 2, because you're given that. How much 1 hour costs and stuff for each of these processes. That's at least my level of thinking with it. So I've made a simple table here. Chemicals listed and at the bottom the cost. So process 1 and process 2, 3 units and 1 unit for A, 1 unit for B, and 1 unit C from process 1, no units from process 2. It costs $4 per hour for process 1. $1 per hour for process 2, But you can see that it's going to be, you have to consider it. The problem considers this. Process 2 is a lot cheaper, but you get only 1 unit of A and 1 unit of B. You get no unit of C. So process 1 gives you all units, and it gives you overall 5 units instead of just the 2, but it's a lot more expensive. But you can only get chemical C from process 1, so you do have to use it. So the hourly cost is Z equals 4 times x1 plus 1 times x2, because obviously it just does cost. And that's all we're worried about, is minimizing cost here. So minimum Z equals 4x1 plus x2. That's all it is. Daily production requirements, so chemical A production equals 3 units times x1 plus 1 unit x2. That's how much is produced. It's however many units times x1 plus 1 unit times x2, so the 2 process hours of them, the hours of the process. So it must be greater than or equal to 10, so we just get 3x1 plus x2 greater than or equal to 10. Same thing with this and that. So you get x1 plus x2 greater than or equal to 5 and x1 greater than or equal to 3. But it's all from reading the problem just a little bit carefully. And the LP is then minimum Z equals 4x1 plus x2. So I said here. Then these are the constraints, plus we also have x1, x2 greater than or equal to 0. And I even put chemical A, B, and C as the constraints and where they come from. Yeah, so we solved that LP now. Same way as the other one, the Farmer-Jones problem. Only difference is we consider it as a minimization. So 3x1 plus x2 equals 10. You solve for the x1, x2 intercepts. Then you do 0 plus 0 greater than or equal to 10. That's not the case, so it can't include 0, 0. x1 plus x2 equals 5. You get 0, 5, 5, 0. And then you get 0 plus 0 greater than or equal to 5. That's not the case, so it's also going to be. Then x1 equals 3. 0 greater than or equal to 3. No. So it can't. None of it includes the point 0, 0. So we're going to go away from that point. We're going to shade away from it. As you can see, I draw the lines like usual, and then we have the stars as the colors. So x1 plus x2 equals 5. It's going to be this area, and then 3x1 plus x2 equals 10. That. So just this. Then x1 equals 3. So it's this whole region. So yeah. It's the black region. The feasible region is all of that. So it's a big one. The difference is it's minimization, so you want to get the lowest amount. So just A, B, these 2 points are all that there is. A and B here. Or the edges, as you will. The points. And seen on graph B is just 5, 0. Because we got the intercept, so it's just the point A we have to figure out. So we'll use x1 equals 3. And x1 plus x2 equals 5, and this is a very easy one to solve. So x1 equals 3, and 3 plus x2 equals 5, so you get x2 equals 2 and x1 equals 3. So A is 3, 2, and B 5, 0. Z equals 4x1 plus x2, so minimum Z equals 4 times 3 plus 2 equals $14, and minimum Z equals 4 times 5 plus 0 equals $20 for A and B points, respectively. $20 and $14. You take the smallest of these points, and $14 is that. So optimal solution is x1 equals 3, x2 equals 2, and minimum Z equals $14. So it's 3 hours of process 1 and 2 hours of process 2 to get minimum cost of $14. And that's how you solve those types of LPs with 2 variables.